this manual wheel right here and just crank it down. This wheel, the front of this wheel is representing whatever the boring bar is doing. If the front of this wheel is going down, then the boring bar is going down. If the front of this wheel is going up, then the boring bar is going up. It moves so slowly, sometimes you can't really see what's happening there. Okay, now, we have a couple options here to center the bar in the cylinder. We can do it on the least worn portion of the cylinder, on top of the ring ridge, or we can do it under the ring ridge on the most worn part of the cylinder. And we have to make that decision, which way are we going to bore this cylinder. Okay, here's the pros and the cons. On top of the ring ridge represents the location of the cylinder where the factory, in this case, has never been bored. The factory machined that cylinder. Nothing's worn it, nothing's distorted it. The top of the ring ridge represents the location where the factory machined it. Under the ring ridge represents any outer round wear that we may have in this cylinder. My approach to boring a cylinder is take the least amount of material out in order to create a straight round cylinder. If you have an outer round cylinder, we know that not all of the wear is going to be equal on all four sides of the cylinder. It's going to be offset a little bit. If it's offset enough, if we center up on the ring ridge and bore out the cylinder, we might miss some of that wear. So we might have to bore that cylinder bigger in order to catch all of that wear. Whereas if we center up where the wear is, under the ring ridge, then we can center up in the middle of all of that wear and potentially bore that cylinder maybe 20 and clean up all of it without having to go maybe 30 or 40. You understand what I'm saying there, guys? But we compromise the center line of that cylinder. So we have to decide what's more important, the location of that cylinder based on where the factory machined it, or ultimately cylinder wall thickness. That's what we're talking about, right? Not wanting to bore it out too far is preserving cylinder wall thickness. My approach is preserving cylinder wall thickness and boring out the cylinder on the most worn, or centering up rather, on the most worn part of the cylinder so I can bore out the least amount of material. Now I do sometimes move the center line of that cylinder just a little bit, but we're probably talking 3, 4, 5 thou. And without sounding too pessimistic, I'm not real confident that the dude at the factory machined it perfectly in line. With bore spacing and the accuracy of some of the other stuff that we check on the, like the deck surface, for instance, we know that the standards that the factory has to use when they're cranking out thousands of these a day aren't as tight as we can hold them, okay? So I'm not even putting a lot of value in the fact that the cylinder's in the right location to begin with. I'm more worried about cylinder wall thickness. So that's my opinion. You guys can actually make the decision when you get ready to bore your block, which is more important. Moistness is your block. What do you say? Huh? Where are we going to center it up? Okay, you need to watch your video later because you kind of missed the point on that deal. I'm going to interpret that to say you want to center it up underneath the ring ridge where the wear is, right? Okay. But you bring up a good point with piston material. He literally has piston material stuck to the cylinder wall. The piston burned. When the piston burns, some of the aluminum got stuck to the cylinder wall. If our centering finger hits on top of that aluminum, it's going to push this thing off center. So when we center up in here, we need to make sure we're not on top of that. And if you guys have anything like that in your cylinder, make sure that the centering fingers don't touch it, okay? So to do that, we're going to have to position this thing right about there. Okay, now, when I center the cylinder, I always want this thing floating so it can move. So I've got my float on. I'm going to push the centering fingers out. I'm going to push that bar to the middle of the cylinder. I'm going to turn the float off, or I'm going to turn the lock on, and then I'm going to let go of the centering button. Okay, now that procedure, those steps are super, super important. Never ever have both the float and the lock on at the same time. Never ever try to lock it down without centering it. Okay? So for instance, if we're floating it, we center it, we turn the float off. Oh great, that looks good. Let go of the centering fingers and then lock it down. There's a split second there where this thing could actually move. We want to have those centering fingers against the cylinder when we lock it down. Okay, now to add to the complexity of that procedure, there's another little issue here. Mr. McCoy started this part of the automotive department in 1971, 72. He bought this machine brand new in 72. That's right, the thing's like 40 years old. Okay? Mr. McCoy, for many, many years, taught his students to float the cylinder, or float the bar in the cylinder, but push it all the way to the back. And then, when you hit the centering button, it pushes out on that rear finger and situates it in the cylinder in the right location. Now there's some benefits to that, but there's a big drawback to that. After years and years and years and years of Mr. McCoy doing that, the rear centering finger wore more than the front two centering fingers. So right now, if we center it up with those three centering fingers, because the back one's worn more, the bar is actually going to be too far back in the cylinder. We have to compensate for that. We're going to compensate for that wear with this feeler gauge. This is a 7 thousandths, no, 4 thousandths feeler gauge. This 4 thousandths feeler gauge is going to go behind that rear finger to compensate for the wear that that rear finger has on it. Okay? Why don't we just replace the rear finger, because it's not actually the rear finger that's worn. It's the part that pushes on the rear finger in this machine right here. That part's no longer available. All right? So, quite literally, while floating it, while shoving this down in between the cylinder and the rear centering finger, now my feeler gauge is in between the rear centering finger. I'm going to turn off the float, turn on the lock, let go of the centering fingers. Now this thing's in place. Okay? So a little non-factory procedure right there. The reason I spend the time I do to tell you the Mr. McCoy story is because I for a couple of semesters, I just taught that this was part of the setup. And then I got a phone call from a machine shop owner. And he says, hey, you sent me a student that tried to put a 4th thou feeler gauge behind the centering fingers on my boring bar. What are you teaching these guys? And that student misinterpreted this procedure and thought you had to do this on every single machine in Kern County. No, you only have to do this on BC's boring bar. Okay? So don't go get a job and stick a 4th thou feeler gauge behind it. Now, another little procedure that I have learned the hard way. I was using a machine similar to this in a shop right after I graduated from BC. I went through the setup procedure just fine, had it all locked down, got ready to bore the thing, only I didn't know that the little airlock that was locking this thing down to the table had failed. So the minute I started cutting that cylinder, this thing's just sitting there. It's not locked down. And it starts dancing around like this, and it knocked the crap out of the cylinder. Okay? So another little thing that I've picked up, having learned that lesson the hard way, is right now with it in the lockdown position, I give it a little shove. Make sure the air compressor is turned on, and we actually have air pressure locking this thing down. Make sure the valve and the toggle switch and all the mechanism that's holding this thing down is actually working. If it moves, you're getting ready to have a problem. Does that make sense? Okay. We're centered up, we're locked down, we're ready to machine this, but we need to set up our cutter for it. Is everybody okay with what we've done so far? Okay. We're going to pull this up. Again, front of the wheel's doing whatever the boring bar is doing. Okay, in this cabinet over here, you You've got 4 different cutters. You got 2 that are painted red. They both serve a very important purpose. The top one has a 45-degree angle cut on it for chamfering the top of the cylinder when we're done boring it out. The bottom one has a 90-degree angle cut on it for creating a step at the bottom of the cylinder if we're installing a repair stick. Neither of those are used to bore out the cylinder. They're both special cutters, that's why they're painted red. In between here, we've got 2 cutters that aren't painted. These are exactly the same cutter, machined with the appropriate angle combination to bore out the material and remove the material from the cylinder. They're 2 different sizes. This one's for larger bores, this one's for smaller bores. We're going to obviously use this one to work on a little small bore.
Small baby.
We have even more adjustability because there's a shaft coming out of the back of the tool holder that we can loosen up and slide in and out to accommodate, again, larger and smaller bore sizes, okay? And we're going to see how that comes into play. We have such a small bore here, I'm guessing this thing's going to have to be just about bottomed out, so we're just going to put it in there. And then the last part of this is we've got a little spring-loaded finger that pops out here that's going to help us when we actually set the diameter of it. Now, the diameter of the cylinder we're getting ready to machine is determined by how far this cutter sticks out of the boring bar. The farther out it sticks, the bigger the hole it's going to cut. The farther in it sticks, the smaller the hole is going to cut. Now that's important to remember because as we go through this setup procedure, there's about a dozen ways you can screw up and cut a bigger hole. There's a grand total of 1 way you can screw up and cut a smaller hole. Now if you're going to mess up, would you rather cut a little too big of a hole or a little too small of a hole?
Smaller.
Obviously. It's easier to remove material than it is to put it back, right? You guys are going to see a bunch of different ways we can goof and cut too big of a hole if we're not paying attention, if we're not careful when we set this thing up, okay? All right. So the tool we're going to use to establish the diameter of our cylinder and set the diameter of our cutter bit is this guy right here. This guy right here reads kind of like a micrometer, only a little bit different. I'll explain that more in a minute. It's got this finger that goes into the boring bar and seats against a socket. And depending on where we have this set, when this goes in and seats, the cutter bit is going to hit the face of the tool and establish the location of the tool, how far out, how far in. So a very fine adjustment here. For that fine adjustment, we need a very fine, precise setup tool. The setup tool reads like a micrometer, only instead of a 25 thousandths on the thimble, here this one reads 50 thousandths. Okay, I've already told you 2 ways you can screw up and cut a bigger hole than you wanted to. One, if there's any dirt down in this socket where the tool's going to go in and bottom out, the tool's not going to go in all the way, it's going to be sticking out too far, the cutter's going to stick out too far, bam, you bored a bigger hole. 2, if we want to set, I'll use a real common example. You got a 4-inch bore. If you're going to bore the cylinder 30, if you want your final bore size to be 30 thousandths over, what size are you going to bore the hole? 25. So if you grab this thing and say, okay, reads like a micrometer, right? 1 revolution on the micrometer is 25 thou. Now that's 4.025. It's not 4.025, it's 4.050. Because it's 50 thousandths for every revolution on the micrometer. Okay? So down, bam, you bored a bigger hole because you didn't read the micrometer, the setup tool. I need to stop calling it a micrometer because it's not a micrometer. The setup tool reads like a micrometer, kind of 50 thou per revolution, not 25. Okay? All right. What size are we going to bore that one? 20 thou over what? I need to know standard bore size. Huh? In American English. It just doesn't read it in millimeters.